Hello. How good are you at critiquing your own work? If we spend a lot of time on something, it's pretty easy to assume or hope that it's really good. Or we might be critical of our own work or not have much confidence in it. For sure, we don't want to be like George Box once said about statisticians, that they're like artists who tend to fall in love with their own models. So we don't want to fall in love with a mathematical model that isn't great, but we also want to recognize something that has value. So in this section, we're going to analyze our models, and we're going to look at some general questions you can ask when you're trying to decide whether you have a good model or not, and what the strengths and weaknesses of it are. So let's look at some of those questions right now. The first thing, of course, to always ask is, does the model make sense? Does it answer the question? You may have a good answer to a different question, but is it the one that satisfies the original real-world question you're interested in? Another thing that we'd like to do if we can is, can we test the model? Maybe there's some data that you've collected that you can test it against, or you already have in creating the model. Sometimes that happens. Or maybe there's some other resource that has their own solution, and so you can compare. Now, just because you have different answers doesn't mean one is right and one is wrong, but it is another way of checking your model. Now, if you have data, there's a few more concrete things we can do. For example, how good is the fit? And there's a couple of different ways we can talk about that in terms of looking at trends of error and the amount of error and so forth. So we'll come back to that one. And along those same lines, we can ask ourselves, is it optimal? Right? Or is it overfitting? So there's a variety of issues to think about with data. Another thing to look at is sensitivity to either the parameters or the inputs. And is it enough to cast some doubt about our model? Also along these lines is, can we quantify the total error? So it would be nice when we have a final model that's predicting some sort of number or some sort of value, that we'd like to have a plus or minus attached to that. And where that plus or minus comes from will depend on all the other errors that went into making the model. Maybe a challenge to get a good value for that, but we at least want to think about it. In fact, you might even consider an interval. As with anything, we always want to think about strengths and weaknesses and limitations. So maybe you have a good model, but maybe it's only good in certain conditions. And so that would be a limitation we would want to write down. And then finally, are we confident in our model? Or do we need to try again? So as we mentioned, the modeling process can sometimes be thought of cyclical. And so this is one of those times when you might ask yourself, all right, do I need to back up a step? Do I need to go all the way back to the beginning and re-evaluate my initial assumptions? Or if we like it, we can move on to the next stage. And at the end of this stage, then we should have a better feel for which way to go. So let's talk about a few of these in more detail. So we talked about with data and how good of a fit. So one way to answer that question is to look at residual plots. And basically a residual plot is to just plot the difference between the data and the model. So let me give you an example. So the blue dots here that are curved represent some sort of data that we're trying to model. And our initial attempt is to use a straight line to model it. And so we can see there's some error here. There's a difference. The model is below the actual data point. And so the error then is going to be negative. And so this point here represents that distance. So whatever this change in y is, represents this y value right here. And of course, you can see that where we have positive residuals correspond to where the model was above the actual data. And the problem here is there's a trend. And a trend is bad. Because that means there's some underlying feature to the data that is not being captured by our model, and so there's a trend of the data. So if you always have a positive errors on one part of the x-axis and negative on the other part of the x-axis, or this one's a little more complicated trend, regardless, it shows that something's not quite right. Now, if you look at the magnitude of the error, if this is small and you're willing to accept that, maybe you accept it and move on, but it still shows that we're missing something. So let's take a look at the same data, but with a different model. So model 2, still the orange dots, now we're using a curve function, a quadratic. And notice this is not a perfect fit either, but it does seem to be capturing the trend better than the straight line. And we can see that for a couple of reasons. Notice the error seems to be more random. So random residuals. And the other thing is we can look at the magnitude of the error. So here our error ranges from -10 to 16 or so, and here everything is between -5 and 5. So there's two indicators that we have a better model. It's smaller in magnitude, but also more random, because there's probably going to be some noise in our data, right? Most often there's going to be measurement error or something that goes on that is hard to quantify, especially with a simple model. And so if you see a little bit of error like that, that's okay. So that's residual plots. Another thing that we can talk more about in future sections is number 5 is quantifying the total error. And for now, I'll just say that there's 3 main ways of thinking about it, although there's certainly many more formulas out there to use. But one is to look at absolute error. So in that case, we would just want the magnitude of the error to be as small as possible, right? Look at the worst case scenario. What is my worst prediction, my worst fit? And I want that data point to be as small as possible. So we see here some 15, 16. We would like that number to be smaller to have a better fit. And you can talk about absolute error either as an average or a maximum. So maybe we care more about the worst case scenario, or maybe we care more about the average of all the data points. Now, sometimes absolute error, if you're doing, say, population in the United States, you could be off by 1 million people. That seems like a lot, but percentage-wise, that's not so much. And so that's why percent error is another approach. And again, you can do the same scenario, worst case scenario, or just the average. And then the third scenario that we're going to talk about is the squared error. And that can either be a sum or a mean. And when we talk about optimal, when we talk about kind of the optimal fit, we're actually going to base that on the squared error, but we'll come back to that in a section in chapter 2. But for now, just be aware that there's there's at least these three ways of thinking about how good of a fit you have and giving a numerical value to it so you can have a way of comparing different models or even reporting, here's how good the fit is we're always within 10% or we're always within 5% of the data we have, something like that. Another thing we talked about was sensitivity. This is a situation where you might have a good model, but it's very dependent on the value you use within it. And so in this case, we just want to be aware that there is some sensitivity. We got a glimpse of this in the last section where changing one data point had a dramatic effect on the prediction that a quadratic would pass through those points. Now, keep in mind, we can limit that if we have more than 3 data points. That was a very simple example. If one has a lot of data, then 1 point probably won't change our model that much. But nevertheless, even a good model can be sensitive to data. So for example, we'll consider a famous example, and that's the following, is that I have a sub n plus 1 is equal to r times a sub n times 1 minus a sub n. So this is a difference equation, and we'll say more about those later. And we'll say our a naught is 0.5. And so with a starting value, of 0.5, we'll start with 0.5, not 0.05. And we'll use this recursive relationship to define future values. And what we would like to see is how does this model behave for various values of r and also as my initial value changes. So let me show you an example of a model that is what we might call stable versus sensitive. Here's a spreadsheet, and I won't go into all the details of how we created it. That's for a section in chapter 3. But right now we have a starting value of 0.5, and then that coefficient r, I'm going to use 2.8. And notice what this formula does right here in the spreadsheet is it just takes that coefficient and then it multiplies it by the previous a value times 1 minus that same a value. And then it iterates that for 20 times. And notice that this is an example of a stable model because if I use 0.5, then it tends towards somewhere around 0.64, 0.643. And if I happen to be a little bit off, maybe it's really 0.4, then the model doesn't change at all. And if I was way off, say 0.1, because our a naught can be anywhere between 0 and 1 in this case, then even with something as far away as 0.1, all right, it takes a few points to get to that equilibrium, but I still level off to about 0.643. But consider the scenario where I have 3.95 and we start with 0.5. Well, now notice you can see there's a lot more chaotic behavior here. So this is an example of chaos. And you can see that there's no trend, but even if we just care about the 20th value, at A20, I get 0.908. But even if I change this slightly, like say to 0.499, then that 20th value changes dramatically. And of course, the graph looks quite a bit different by the time you get to the end. And if we changed it again to 0.498, so these are smaller changes than we tried before, then notice it looks very different again. Now we're down to 0.348. So this is highly sensitive to our original condition. And so the famous example of this is called the butterfly effect, that if a butterfly flaps its wings in China, then you'll get a rain shower in New York. The idea is that something that is very small change, but if you wait enough iterations in your model, then that, because it has a chaotic nature, then you're going to get wildly different outcomes. And the problem is, if it's that sensitive, then we can't have much confidence in our initial model because unless we have really good measurement tools, we can't have confidence that that 3.95 or that 0.5 are accurate enough numbers to use for long-term predictions, or maybe even short-term predictions. So that's just a few examples. We will work through this stage of the process with a concrete example in our next video. So we'll see you there.